Hello friends, myself R.D. Mahajan, Assistant Professor, MIT Aurangabad, presenting my video on the topic of inverse Laplace transform, and in this I will explain how we can use the theorems or the properties to find inverse Laplace transform. In my last video, I have discussed some standard results to find the inverse Laplace transform like this. Inverse of 1 by s is 1. Inverse of 1 upon s minus a is e raised to at. Inverse of 1 upon s square plus a square is 1 by a sin at. Inverse of s upon s square plus a square is cos at. Like this. Total 7 standard results I have discussed. Then we try to see the theorems to find the inverse Laplace transform. The first one is shifting theorem. Its statement is like this: if inverse of f bar of s is f of t, given or we can obtain it, then inverse Laplace of f bar of s minus a means s replaced by s minus a or s replaced by s plus a, then it is equals to, when it is f bar of s minus a, f of t we have to multiply by e raised to at, and when it is f bar of s plus a we have to multiply f of t by e raised to minus at. This is the indication of that it is the problem for shifting theorem, if s replaced by s minus a or s plus a. Second theorem, multiplication by t theorem. Statement is like this: if inverse of f bar of s is f of t, then inverse Laplace of nth derivative of f bar of s as minus 1 raised to n t raised to n f of t. And using this we can obtain sub result. If we consider the value of n as 1, means inverse of f dash of s, first order derivative, is minus t f of t, or t f of t into minus 1. This is the result. Next theorem: if inverse of f bar of s is f of t, then inverse of f bar of s into 1 by s, or 1 by s into f bar of s, its inverse is integral from 0 to t f of t dt. And next, division by t using that property. Statement: if inverse of f bar of s is f of t, then inverse Laplace of integral from s to infinity of f bar of s ds as f of t by t. And the last one more, inverse of f bar of s is f of t, then from this result and using this shifting theorem, a combination of these two theorems, we get inverse of 1 upon s minus a that raised to n is equals to this result, t raised to n minus 1 upon gamma n multiplied by e raised to at if it is s minus a, and if it is s plus a we have to multiply by e raised to minus at. Or we have the result e raised to at t raised to n minus 1 upon n minus 1 factorial if n is positive integer. Therefore, all these are the statement of the theorems which we can use to find the inverse Laplace. Therefore, I will discuss some problems how we can use this theorem to find the inverse Laplace. Find inverse Laplace of 1 upon s minus 4 and that is to 3. Okay. Here it is a problem of shifting theorem, as s is replaced by s minus 4. And by that shifting theorem, we have inverse Laplace of 1 upon s raised to n. Here it is s cube. N is positive integer, and then as n is positive integer, we apply this one, t raised to 3 minus 1, that is 2, divided by 2 factorial, and we call this as f of t c. Okay, then by shifting theorem, therefore inverse Laplace of 1 upon s minus 4 and bracket raised to 3 is equals to, as s is replaced by s minus 4, we have to multiply it by e raised to 80. A is here 4, therefore it is e raised to 4t into that f of t. What is f of t? It is t square upon 2 factorial. 2 factorial is 2, and this is the required inverse Laplace transform. A combination of this result and that shifting theorem. Okay. Find inverse Laplace of one upon s plus 2 raised to 1 by 2. Again, here s is replaced by s plus 2, means it is problem of shifting theorem. And to obtain this inverse, we take this help of this result as well as the shifting theorem. Therefore, we have inverse Laplace of s 1 upon s raised to 1 by 2. Here that power n is not positive integer, and therefore we have to apply this result. It is t raised to n minus 1, t raised to 1 by 2 minus 1, or consider here as 3 by 2. Therefore we find out this as s raised to 3 by 2 as t raised to 3 by 2 minus 1 divided by gamma n, gamma of 3 by 2. Okay, and therefore it is equals to t raised to 3 by 2 minus 1, finding LCM or cross multiplication, 3 minus 2 we get 1 by 2 divided by this gamma n we write down in the form of gamma n plus 1. Therefore that 3 by 2 I can write down as 1 by 2 plus 1, and therefore it is equals to t raised to 1 by 2. Gamma n plus 1 is n gamma n, therefore 1 by 2 gamma 1 by 2, and the value of gamma 1 by 2. In next step we substitute as root pi, and therefore it is equals to t raised to 1 by 2. This 2 goes to numerator divided by root pi, and we call this as f of t. Okay, and therefore inverse Laplace of 1 upon s plus 2 raised to 3 by 2 is equals to, by shifting theorem, it is e raised to, here it is s plus a, therefore e raised to minus 80, a is here 2, 2t into f of t, and f of t is 2 t raised to 1 by 2 divided by root pi. Answer for this inverse. Find inverse of s plus 1 whole square plus 2 square here s is replaced by s plus 1, means it is a problem of shifting theorem, and therefore to apply that shifting theorem, first of all we find out the inverse of 1 upon s square plus a square by this, and therefore we have inverse Laplace of 1 upon s square plus a square 2 square 1 by a, here a is 2, therefore 1 by 2, and sine of 80, sine of 2t, and we call this as f of t, say. Okay, and therefore inverse Laplace of 1 upon s plus 1 bracket square plus 2 square is, by shifting theorem, e raised to minus at minus t into f of t. Okay, and therefore it is equals to e raised to minus t, and f of t is 1 by 2 sine of 2t. Therefore, by shifting theorem, we get this inverse, or that is e raised to minus t sine 2t divided by 2. Next example, example number 4th. Find inverse Laplace of s minus 2 divided by s minus 2 bracket square plus 9. Okay, in both numerator and denominator, s is replaced by s minus 2, means it is a problem of shifting theorem. Therefore, first of all we find, if we neglect this 2, it becomes s upon s square plus 3 square, applying this standard result. Therefore, we know, or we have inverse Laplace of s upon s square plus 3 square as cos of 80 cos of 3t, and we call this as f of t, say. Okay, and therefore by shifting theorem, inverse Laplace of s minus 2 divided by s minus 2 square plus 3 square, it is s minus a type of term, therefore it is e raised to at, a is here 2, therefore it is e raised to 2t into f of t, and therefore it is e raised to 2t into f of t. What is f of t? It is cos of 3t as the answer for this inverse. or this is the inverse Laplace transform of that function. Find inverse Laplace of okay. Here s is replaced by s minus 2, means once again it is a problem of shifting theorem. Therefore, first of all we find removing this 2 or neglecting that 2, it becomes 1 upon s square plus a square. Consider here minus. Therefore, it is s square minus a square. Therefore, using this, we have inverse Laplace of 2 upon s square minus that 4. 4 means 2 square. This 2 I can take outside as it is constant term. Inverse of s square minus a square is 1 by a. 1 by a is here 2. Therefore, 1 by 2 into sin h at. Sin h is here 2. Therefore, 2t. And therefore, 2 to get cancelled, we get sin h 2t. And we call this as f of t. And therefore, by shifting theorem, using shifting theorem, inverse Laplace of this 2 upon s minus 2 bracket square plus 2 square minus 2 square. As per that theorem, it is e raised to minus, here it is minus, therefore e raised to 80, e raised to 2t into f of t, and therefore it is e raised to 2t, f of t is sin h 2t. Okay, this is the required inverse Laplace. One more. Find inverse Laplace of s plus 1 bracket square minus s 49. Okay. Therefore, both in numerator and denominator, s is equal by s plus 1, means it is a problem of shifting theorem. First of all, we neglect it 1, remaining term is s upon s square minus 7 square. Applying this standard result, therefore we have inverse Laplace of s upon s square minus 7 square is nothing but cos h 80 is a 7, therefore 7t, and we call this as f of t, say. Okay, and therefore by shifting theorem, inverse Laplace of s plus 1 divided by s plus 1 square minus 49 or 7 square is equals to, it is plus a Therefore, it is multiplied by e raised to minus 80 term. It is e raised to minus 80. A is here 1. Therefore, e raised to minus t into f of t. And therefore, it is equals to e raised to minus t into f of t. What is f of t? It is cos h 7t as the required inverse Laplace. Find inverse of inverse Laplace of 1 upon s into s square plus 1. Okay, and therefore we use that theorem. We know that inverse of 1 by s into f bar of s is integral from 0 to t f of t dt. Okay, and therefore here f bar of s we consider as 1 upon s square plus 1. Find its inverse. Therefore, inverse Laplace of f bar of s means the inverse Laplace of 1 upon s square plus 1. Using this standard result, it is 1 by a is 1, therefore 1 by 1 sine of 80 sine of t, and we call this as f of t, say. Okay, and therefore it is inverse Laplace of 1 by s into that f bar of s. F bar of s is here s square plus 1, and as per this theorem, it is integral from 0 to t f of t dt. Okay, it is integral from and therefore it is equals to integral from 0 to t f of t is sin t dt. Finding the integration of this, performing integration of this with respect to t, integration of sin t is minus cos t, and limits from 0 to t. I will cancel that minus 1 by changing the limits. Therefore, this become upper, this become lower. Cos of 0, 1 minus cos t. Okay. Therefore, this is the required inverse Laplace transform. One more example of this type. Find inverse Laplace of 1 by s into 1 upon s minus 2. Okay. If we consider this part as f bar of s multiplied by some 1 by s, we have to apply this. Therefore, we have inverse Laplace of 1 upon s minus 2 as by this it is e raised to 80, a is 2, we call this as f of t, and therefore inverse Laplace of 1 by s into this 1 upon s minus 2 by this property or theorem, it is integral from 0 to t of f of t dt, and therefore it is equals to integral from 0 to t. F of t is e raised to 2t and its integration, and therefore it is equals to integrating this with respect to t, we get e raised to 2t by 2, limit from 0 to t, 1 by 2 constant outside, upper minus lower limit, upper limit it becomes e raised to 2t minus lower limit e raised to 0, we get 1, and this is the required inverse Laplace or the required answer. Last example, find inverse Laplace of s plus 1 divided by s square plus s plus 1. Okay, in numerator we have s plus 1 term, means s replaced by s plus 1, means in denominator also we must have replace s by s plus 1, but it is not given in that form. Therefore we try to rewrite this denominator term s square plus s plus 1 as, we try to find out the last term by considering this first two term, and formula to find the last term is middle term square divided by 4 into first term to make the perfect square. And here middle term is s, therefore square of it 4, first term is s square get cancelled, we get 1 by 4. Therefore add 1 by 4 and subtract 1 by 4. Therefore here it is s square plus s. Here I will add plus 1 by 4. Subtract the same number, minus 1 by 4. Adding and subtracting the same number, and plus this original 1. And therefore if we rewrite it, this first three terms is a perfect square of, therefore if we square this, a plus b whole square, s square, twice ab, we get s, and b square, 1 by 2 square, 1 by 4, and plus 1 minus 1 by 4, 1 minus 1 by 4, 4 minus 1, we get 3 by 4. Okay. Okay, and therefore it is s plus 1 by 2 whole square plus 3 by 4 we write down in the form of square, therefore it is root 3 by 2 bracket square. Okay, and therefore this s plus 1 upon s square plus s plus 1 I can rewrite as s, here s is replaced by s plus 1 by 2, therefore convert that one as 1 by 2 and plus 1 by 2, so that we get original 1, and divided by this s square plus s plus 1 is in this form, new form, therefore it is s plus 1 by 2 square plus root 3 by 2 square. Okay, and therefore inverse of this means inverse of this. Therefore next step, inverse Laplace transform of s plus 1 s square plus s plus 1 is nothing but inverse Laplace of this. First is and plus 1 by 2 divided by s plus 1 by 2 square plus root 3 by 2 square. Okay, we take a separate division, this divided by this and this divided by this, and then find two separate inverse. Therefore first is inverse Laplace of s plus 1 by 2 divided by s plus 1 by 2 square plus root 3 by 2 square and plus 1 by 2 constant outside, inverse Laplace of 1 upon s plus 1 by 2 square plus root 3 by 2 square. Okay, here s replaced by s plus 1 by 2, here also s replaced by s plus 1 by 2, means it is the problem of shifting theorem. Therefore applying that shifting theorem, it is e raised to minus at minus a is 1 by 2 times t into inverse of remaining. What is the remaining term? S upon s square plus a square. S upon s square plus a square, its inverse is cos of 80. Therefore it is cos of a is here root 3 by 2 times t. We get the inverse for this by applying shifting theorem. Here also same shifting theorem, 1 by 2 as it is. It is s replaced by s plus 1 by 2, therefore it is e raised to minus 80 into f of t. What is f of t? Inverse of 1 upon s square plus a square, and using this it is 1 by a 1 upon root 3 by 2 into sine of 80. Sine of 80 is root 3 by 2 times t. And from this two term I can take e raised to minus t by 2 common, and remaining is cos of root 3 by 2 t, and this 2 to get cancelled. It is 1 upon root 3 sine of root 3 by 2 t as the required inverse. Therefore, with the help of all this example, I have explained how we can use that theorems, mainly a shifting theorem. If you are watching my videos, please like it, share it, as well as subscribe my channel for new updates or latest update. Thank you.